Let's say that you need to carry a long ladder down a hallway and that there's a corner in the hallway. Will the ladder go around the corner? Well, that depends on several things. It depends on the length of the ladder, and it depends on the width of the hallway. And what if part of the hallway is narrower than the other part? This is a classic optimization problem in Calculus 1. We can measure the widths of the different parts of the hallway. It turns out that that information and a little bit of calculus is all we need to be able to figure out what the longest ladder is that will fit around that particular corner. Let's say in our case we've measured this hallway and we know that it's 8 feet wide here, but in the other part of the hallway it narrows to only 5 feet wide. Now that we know that, we can augment our diagram a little bit and create two right triangles. There's a right triangle here and a right triangle here, and we're going to use those two right triangles to finish out this problem. Another thing to note is that what we essentially have here is two parallel lines, and the ladder is the transverse between those two parallel lines. So the other thing we can note in our diagram is that these two angles are the same angle. Actually, there's a third line down here that's parallel as well, and that's what lets us get away with stating that those two angles are equal. Okay, let's make some other observations. We're going to call the entire length of the ladder L, but we're going to break it up into two parts. I'm going to call this long piece here L1 and the shorter piece L2. So another way to write capital L, the length of the ladder, is as L1 plus L2. That'll come in handy later on. So now I have labels for one angle and two sides of two different right triangles. For my top right triangle, I can write sine of theta equals 5 over L2. Because the width of the hallway is 5, and that's the side opposite theta in that triangle. Using the same reasoning for the other triangle, this one down here, I can say cosine of theta equals 8 over, this time, L1. Notice that in this particular diagram, L1 is shorter than L2. They're different lengths, so it's important to distinguish them. Now what I'm going to do is solve each of these two small equations here, this one and this one, for L1 and L2 respectively. If I multiply both sides of my sine equation by L2 and divide both sides by sine theta, I get L2 equals 5 over sine theta. If I do the same thing with my cosine equation, I get L1 equals 8 over cosine theta. So now I can write L as L1 plus L2 in this way. L1 is 8 over cosine theta plus L2 is 5 over sine theta. So this is a different expression for the length of the ladder. The thing is, we know that to minimize or maximize a function, we need its derivative. What I have now in L is a function in theta. So the variable I'm working with here is theta. In order to maximize the length of the ladder or minimize the space it has to pass through, I need to take the derivative of this function. I need to find L prime of theta. I could either write 8 over cosine of theta as 8 secant of theta and 5 over sine as 5 times cosecant, or I could use the quotient rule. In this case, I'm going to use the quotient rule, but I'd like to argue you could do it either way. The quotient rule says that the derivative of 8 over cosine is cosine times the derivative of 8, a constant, minus 8 times the derivative of cosine, which is negative sine, all over the square of the denominator. And now I'll do the same for the second term. The derivative of 5 over sine is sine times the derivative of 5 minus 5 times the derivative of sine, which is cosine. And that's all over the square of the denominator. Now I'm going to find a common denominator, and that will necessarily be sine squared cosine squared as a product. So I'll need to introduce cosine squared in the second fraction, and I'll need to introduce sine squared in the first fraction, so that I have sine squared times cosine squared as my common denominator, and that gives me, once I've eliminated that this term is 0 and this term is 0, that gives me sine squared times a negative is a positive, so times 8 times sine is 8 sine cubed, and that's all over sine squared cosine squared. And to that I'm going to add cosine squared times negative cosine squared, which is minus 5 cosine cubed of theta. Since I'm minimizing or maximizing, I want this derivative, L prime of theta, to equal 0, because it's when it's 0 that I can find the values of the variable where those maximum and minimum values occur. So now what I'm going to do is take this expression, 8 sine cubed minus 5 cosine cubed, all over sine squared cosine squared, and set it equal to 0 and solve it. In order to do that here, I'm going to need to erase the screen and give myself some more space. Okay, there's that same expression as I had before, and what I'm saying now is that L prime, that derivative, is equal to 0. Instead of saying equals 0 and adding that to the whole expression up here, the other thing I could have done is just replace this L prime of theta with 0 and solved it that way. And instead of messing things up now, I think what I'm going to do is just erase this left-hand side, which leaves me with the equation 8 sine cubed minus 5 cosine cubed all over sine squared cosine squared equals 0, and that's what I need to solve. If a fraction is equal to 0, then its numerator is equal to 0. So I can take this expression I have here and rewrite it this way. 8 sine cubed minus 5 cosine cubed equals 0. And then if I add 5 cosine cubed to both sides, I get 8 sine cubed theta equals 5 cosine cubed theta. Okay, we're trying to solve for theta here, so one of the things that I should probably do is try to get everything that has a theta in it on one side of the equation. So I'm going to divide both sides by cosine cubed, which means that the right-hand side is just now a 5. And I'm also going to divide both sides by 8, which means that the left-hand side doesn't have any constant coefficients in it other than 1. That lets me write sine cubed over cosine cubed, well that's just tangent cubed, as 5 over 8. I can solve this for theta by taking tan inverse, but I don't want to take the tan inverse yet, because what I have here is essentially the tangent of theta quantity cubed equals 5/8. Before I take the tan inverse, I need to have just tan theta. So let's start by taking the cube root of both sides of this equation, or raising both sides to the power of 1/3. That gives me tangent of theta equals the cube root of 5 over the cube root of 8, which is 2. Now I can use tangent inverse to find the angle theta. That's just a calculator problem. It turns out that theta is equal to about 0.707 radians, or about 40.5 2.530 degrees. Which unit you use doesn't really matter because we're ultimately not looking for theta. What we're looking for is L. Remember this expression here that we have for L? L1 plus L2? Well, I've erased it, but remember that L1 was equal to 8 over cosine theta, and L2 was equal to 5 over sine theta. So that's a way to write L. And now I know what theta needs to be in order to minimize the distance. So let's plug theta in. I like radians, so I'm going to use that. I have the value that I found for theta stored on my calculator, and I'm going to put that value into the memory of the calculator so that I'm taking advantage of the highest level of accuracy that the calculator can provide. So while I'm writing 8 over cosine of 0.7 plus 5 over sine of 0.7, when I do this calculation on the calculator, I'm using not 0.7, but 0.70738272215, and the calculator remembers even more. So I'll do this calculation by writing these placeholder approximations in here, but when I actually do the calculation, I'm using the entire calculator's memory for that value. 8 over cosine of 0.7 is about 10.525, and 5 over the sine of 0.707 is about 7.694. If I put these values into the memory rather than adding them here, then when I write down my final result for this problem, I'll have the most possible accurate answer. And at that point, it'll be safe to round off to whatever the level of decimals or significant figures the problem wants. Okay, having done that now on the calculator, I can tell you that the length is 18.21953337 feet. That is the longest ladder I will get around the corner assuming that the corner is at right angles and that the widths of the hallways are 8 feet and 5 feet respectively. Now, ladders aren't sold in partial feet, so it's going to be an 18-foot ladder. That is the longest ladder that can go around that corner. Technically, I could get an 18.2-foot ladder around that corner. It sort of depends on how the question is asked and exactly what level of accuracy you're expected to apply. But that's how you do one of these problems. Sometimes you'll get asked, what is the maximum length of a thin, rigid pole that can be pushed horizontally around a corner joining two pipes, for example? The problem may look slightly different, but this minimize the length of the pole or the ladder or the sofa that can go around a right-angled corner is a classic Calculus 1 application problem. It requires not only that you remember your trigonometry, but that you know that it's an appropriate place to apply it. It requires that you remember how to take inverses of functions. You need to remember how to take a derivative, and you need to know why and when that's appropriate to do. Problems like this often show up on the graduate record exam, which is kind of like an entrance exam for getting into graduate school in a field that requires mathematics. Whatever the reason for you watching this video, I hope this has helped. See you in the next one.